Hello everyone, welcome to our channel Clear and Concise. Let's have a look at this question. With symbols having the usual meanings, the single degrees of freedom system mx double dot plus cx dot plus kx equals to f sin omega t represents. The given equation is mx double dot plus cx dot plus kx equals to f sin omega t. Here m is mass of the system, x double dot represents acceleration, c is damping constant, x dot is velocity, k is spring constant, x is displacement, f is force term, omega is frequency and t is time. In this equation we have damping term as well as externally applied force. So the equation represents forced vibration with damping. Option C is the correct answer. For option A, that is free vibration with damping, there is no external force term exist. Mx double dot plus Cx dot plus Kx equals to 0 represents free vibration with damping. Now, if we look at option B, free vibrations without damping, then the equation further reduces to Mx double dot plus Kx equals to 0. In this equation, there is no externally applied force as well as there is no damping. For option C, we have given equation mx double dot plus cx dot plus kx equals to f sin omega t, which contains both damping term as well as force term. For the option D, forced vibration without damping. In the given equation, just if we delete cx dot term, that is if damping is 0, then equation reduces to mx double dot plus kx equals to f sin omega t, which indicates forced vibration without damping. Moving on to next question. A cantilever beam of negligible weight is carrying a mass m at its free end and is also resting on an elastic support of stiffness K1 as shown in the figure below. If K2 represents the bending stiffness of the beam, the natural frequency of the system is. We have to find the natural frequency of the given system. The natural frequency is given as omega equals to root K by m. Here K is K equivalent stiffness of the system. If we draw the equivalent spring mass system for the given system, we will have a spring of stiffness K2, which is equivalent to the bending stiffness of the beam, and mass m is attached at the end of the beam. So here at the end of spring, which is having stiffness K2, further the mass is resting on the elastic support which is having stiffness K1. This arrangement is similar to the parallel arrangement of spring mass system. So K equivalent is equals to K1 plus K2. As the given system is parallelly arranged, the equivalent stiffness is given as K1 plus K2. Now the natural frequency is equals to K1 plus K2 by mass m of the system. So the option C is correct answer. Moving on to next question. A mass of 100 kg is held between two springs as shown in figure. The natural frequency of vibration of the system in cycles per second is. We have to find the natural frequency of given system in cycles per second. If we observe the given system, the arrangement shows parallel arrangement of springs, because let's disturb the mass 100 kg a little bit. If we pull it downwards, the compression in the spring is same as the extension in the above spring. So the deflections are equal in both the springs. This is possible only if springs are arranged parallelly. For parallel arrangement, equivalent stiffness of the system is given as, the summation of all stiffnesses. So K1 plus K2, that is equals to 20 plus 20, 40 kilonewton per meter, that equals to 40,000 Newton per meter. Now we know angular frequency of the system is omega equals to rho K equivalent by mass of the system, that is equals to square root of 40,000 divided by 100 kg, which yields 20 radians per second. But we need natural frequency of the system in cycles per second. For that, we know omega equals to 2 pi f, which yields f equals to omega by 2 pi, that is equals to 20 by 2 pi, which yields 10 by pi. So the correct answer is option A, 10 by pi. Moving on to the next question. A mass m attached to a light spring oscillates with a period of 2 seconds. If the mass is increased by 2 kg, the period increases by 1 second. The value of mass m is. We have to find the value of mass m which oscillates with the period of 2 seconds subjected to the given condition. Now, in order to find that, we have to know the relationship between time period t and mass m. For that, we know angular frequency omega equals to 2 pi f, which is equals to square root of k by m. Now time period t is given as 1 by f. So if we substitute the above equation, we get root k by m equals to 2 pi by t. So from this equation, t is directly proportional to square root of m, which gives t square equals to c times the m, where c is proportionality constant. By using this equation, we can write t1 square by m1 equals to t2 square by m2. If we substitute the values given in the problem, like t1 is 2 seconds, 2 square by initial mass is, let's assume it is m. Now time period is increased by 1, so 2 plus 1 square divide is by m plus 2, mass is increased by 2 kg, so m plus 2, that yields 4 into m plus 2 equals to 9m, which is equals to 9m minus 4m equals to 8, which leads to m equals to 8 by 5, that is equals to 1.6 kg. So the correct answer is option B, 1.6 kg. Moving on to the next question. Polar moment of inertia of a circular disc is to be determined by suspending it by a wire and noting the frequency of oscillations. So we just need to find the relationship between polar moment of inertia and frequency of oscillations. For that, we know angular frequency omega for discs is square root of kt by I, where kt is torsional stiffness and I is like moment of inertia. So from here we can say that where omega is directly proportional to 2 pi f. So if we rewrite it in terms of f, f is directly proportional to square root of 1 by I. Now f square is directly proportional to 1 by I, which means I is inversely proportional to f square, or I is directly proportional to 1 by f square. The option A is correct answer for this question. Moving on to the next question. In the two rotor system shown in the figure, I1 is less than I2. a node of vibration is situated at? We have to find the location of node along the shaft in two rotor system. For that, first we have to understand what does it mean by a node. Node is a location along the shaft which does not undergo any twist. So at the node, the rotors behave as if it is clamped at the node and vibrate as a two different rotor systems with same natural frequency. So for the above system, F1 is equals to F2. We know F is directly proportional to omega, which is defined as root kT by I, where kT is torsional stiffness, I is moment of inertia. By rewriting this, we have square root of k1 by I1 equals to square root of k2 by I2. Now torsional stiffness K is directly proportional to the g theta by L. So the above equation can be rewritten as g theta by L1 I1 is equals to g theta by L2 I2. Now, so I1 L1 equals to I2 L2. From this equation, we can clearly say that I1 by I2 equals to L2 by L1. So let's assume the node is situated somewhere along the shaft. Now L1 is the distance from rotor 1 and L2 is the distance from rotor 2. Now here I2 is greater than I1, the ratio of L2 by L1 is less than 1. That means the node is situated in between I1 and I2 but nearer to I2 because L2 is smaller than L1 here. So that means the distance from the rotor 1 is more in comparison to distance from the rotor 2. So the option B is correct answer for this question.